Welcome. So in this video, we are going to look at an optimization problem. It's called a fencing problem. So we need to enclose a rectangular field that is 800 meters square with fencing. The field, however, has a building on one side, so we only need to fence 3 sides. Determine the dimension of the field that will minimize the amount of fencing needed. That will also cut down on the cost. Okay, so now the first thing to do in these problems is to draw a picture illustrating the data in the problem. So as you can see, the shaded area here is the building, which fences one side of the field. Then you have the 3 other sides. Obviously, I can create fields that have the same area but with different dimensions. So I can vary 2 quantities to define my field, the width and the length of the field. So I will call those by 2 variables. So it is okay actually just to draw a picture and put your variables. I will guess what they mean. I prefer if you actually write them down and say, for example, let x be the width of the field and y the length of the field. And then typically in these problems, the variables are related. So here, x times y will give us the area, and the area is fixed. So we have a relationship that relates x to y. So here, x times y is equal to a. In this case, a is 800. And then we want to write down the function that we want to minimize. So sometimes we want to maximize it, but here we want to find the field which has the smallest fencing. What do we want to minimize? We sort of want to minimize, it's not the entire perimeter, but I'm still going to call that P of X. Well, it's actually P of XY. But you'll see eventually I will break that down to P of X only. So it's 2x because 1x and another x there. So x plus y. But the idea is that y depends on x, and I can solve this equation here for y in order to express y in terms of x. And here it's going to be 2x plus, if I solve this for y, I get that y is a over x. So overall, p is really just a function of x. So that's why I just wrote p of x here. And this is the function I want to minimize. Of course, x can't be negative, but it can be any positive quantity. So here, x could be anything greater than 0. So this is the domain or the range of the values of x where I want to minimize my function. So it's an open interval. So I will likely use some tests, so maybe the first derivative test or the second derivative test, or just study the sign of my derivative in order to prove that eventually I have a minimum once I find it. Now the next step is to find where the min occurs. This function is differentiable everywhere on this domain, so if there's a min, it's going to occur where the derivative is equal to 0. So my next step is to compute my derivative. So I'll scroll down. So I will compute p prime of x. Well, the derivative of 2x is 2. This is a over x. A is a constant. So so notice I have left a as it is. I could have also replaced a by 800, but you'll see there's a good reason why I've left a just as a parameter for now. So if I differentiate this, well, I'm going to get a minus sign. This is a times x to the minus 1, so it's going to give me minus a x to the minus 2. So minus a times x to the minus 2, so over x squared. I could leave my function like that. I could also put everything over a common denominator if I want to. So 2x squared minus a over x squared. And now I want to solve p prime of x equals 0. So p prime of x equals 0, well, that's going to occur when the numerator here is equal to 0. So that means when 2x squared minus a equals 0. So that's when x squared is a over 2. So there are two possible values for x, but remember that I'm just interested in positive values of x. So x is going to be the positive square root of a over 2. At this point, I could try to compute what x is based on the fact that a is 800. So that's just going to be a square root of 800 over 2. So that's the square root of 400, and 400 is a perfect square. So that's going to be 20. It's meters because the area is in meters squared, right? So this is meter squared. So I found my x. At this point, I'd like to show that this is actually a min for my function. Since I'm minimizing over an open interval, I will study the sign of p prime. So here I will put the sign of p prime and below the behavior of p. So 0 is an important point because I'm minimizing over all positive values of x. So I'm not really interested in what's going on here. Let's say here I could put 20. Well, just to remind you that 20 was obtained by calculating the square root of a over 2, I will also put that here. You'll see why eventually. So 20. Let's see what's going on here. What's the sign of p prime over here? If I go back, and look at p prime, this is p prime. So maybe at this point I could replace a by 800 so that you can see what's going on. So this is 2x squared minus 800 over x squared. And that's actually, if I factor the 2, you see this is x squared minus 400 over x squared. So if I'm between 0 and 20, this bracket here will be negative. This is always positive. This is a positive constant, so I'll have a positive times a negative over a positive. So overall, everything will be negative here. So the sign of p prime is negative. But if I'm above 20, this bracket is now positive. So this is a positive here. But notice that with square root of a over 2, the same analysis holds. So if I'm between 0 and square root of a over 2, this quantity here, this numerator is negative, and that's a positive. So the sign of p prime is also negative no matter what a is, and it's positive here. In terms of the behavior of p, because I have a negative derivative, the function's going down and then goes back up. And that shows you that 20, or root of a over 2, is a minimum. So we've basically proved that we have a min here. So maybe I can write my conclusion. Therefore, x equals root of a over 2, which is 20 in our case, meters, is a local min. So with that, I can write down my answer. So the field should be 20 meters wide by, what's the value of y? Maybe I can compute y on the side here. Y is, what was it? It was a over x. So in our case, it's 800 over 20. So that's 40. So 20 meters wide by 40 meters long. Okay. That's my final answer. So is it a coincidence that y is twice the value of x? Actually, no. I just want to show you this just to finish. So of course the problem is not asking for this, but I just want to show you that it's not a coincidence that 40 is 2 times 20. If you look at y, it's a over x. But if you replace x by root of a over 2, you get that this is a times the inverse of this, so 2 over a times square root of 2 over a. Now a is root of a times root of a, so that's just going to be the square root of 2 times a. And you can write that as 4a over 2. That's the same thing. And if you pull out that 4, it becomes 2 root of a over 2. And that's basically 2 times x, where x is the optimal value. So if you call that, I don't know, if you call that x star, okay, and y star, where x star and y star are the optimal values, well, this is 2 times the optimal x value. So it wasn't a coincidence that this is twice this value. So in fact, if a would have been any number, I don't know, 1287, well, at the optimal point, you would have that the optimal y is twice the optimal x. So this problem shows you that we can actually solve these problems even though there's a parameter. So if we go back to our problem here, okay, we're given that 8 is 800, but it could have just asked what is the optimal, what are the optimal dimensions of the field given some area A. So it is possible that in these optimization problems that you won't be given specific values for your data, but actually just vague parameters. Thanks for watching.